Okay, so I think the first homework is due today. Okay, so yeah, so please submit your homework by the due time. Today we do the discussion on one of the most important property of concrete, okay, which is compressive strength. Okay. Review all the factors about how they will affect the strength of concrete and why. Okay. Many of these things we have discussed before, so today is an overview. Okay. Right. So behavior of materials in compression. So this is the basic information. I think everybody knows that, but let's do a quick review. Mechanics of materials. Okay. So we have concrete cylinder which is under compression. The stress, we call that sigma, right? So which is the force over the cross-section area. Okay. The strain, we call that epsilon, which is change of the length in that direction of the force over the initial length of the specimen. Okay, and when we compress the concrete cylinder in the vertical direction, in the horizontal direction it will expand. Okay, and the ratio about the strain in the x and y direction, okay, is called Poisson's ratio, but that is the absolute value. Okay, so because if we define compression as positive or negative, then tension will be the opposite sign. Okay, so Poisson's ratio always positive, so we take the absolute value. Okay. So for typical concrete, the Poisson's ratio is around 0.18 or 0.2. Okay, so when concrete began to crack, the Poisson's ratio will start to increase, as we can see from here. The figure on the upper right showing us the stress and strain curve for a concrete. Okay, the stress sigma y, and the x-axis will be strain epsilon. Okay, so initially we can see the slope of the curve is pretty much straight, which means the concrete is near elastic materials. Okay. After micro crack occurs, the slope will become smaller. Okay. And after the final strength, okay, the concrete can still somehow resist the load until the final failure here. And this figure shows the volumetric strain, which can be simplified as the strain in the x direction plus the strain in y plus the strain in z direction added together. Okay, but keep in mind, if we define compression as positive, so here epsilon y will be positive. However, epsilon x and z will be negative because they're going to be under tension. Okay. So influencing factors for strength of concrete, that including many things. Okay, as we can see from here, including X1, which has cement characteristics such as the percentage of different compound, microstructure, percentage of gypsum, particle size distribution, water to cement ratio, air content, admixtures. We discussed most of these things in previous lectures, and we know already how this property will affect strength of concrete. X2 is mixing conditions. How much compaction you put in concrete. Curing conditions, X3. The temperature, the time, the moisture, how long you moisture cure the concrete. We discussed before this is also the factor affecting the strength. X4 is manner of testing, which we haven't discussed already. Okay, so I believe this will discuss how the size of the specimen, the geometry of the specimen, set up the machine, these factors, how they affect the strength, tested strength of concrete. Right. The porosity is the most important parameter affecting the strength of concrete. So here, S is the strength of concrete. S0 here is the strength at zero porosity. Okay, and P is the porosity, and K is constant. Okay, so the higher the porosity, the strength will quickly become lower. Okay, but that's a limitation on the strength, even at zero porosity. Okay. And that value shows here. So S0 for concrete is around 34 psi or 230 megapascal. Okay, so that means even the porosity P is 0. The limiting strength is around 230 megapascal for concrete. And here shows the effect of porosity for different type of materials. Okay, so in general, higher the porosity, the strength will be lower. Okay, and for all different type of materials, they all shows the same thing. Okay, for the same type of materials, higher porosity, the strength will be lower as a result. And here shows again the effect of porosity. X is the gel to space ratio, which is basically equal to 1 minus the porosity. Okay. So the porosity is defined as pores over space. Space here means the total space of the concrete. Okay. So gel space ratio X is equal to 1 minus P porosity. So similar things, the higher the gel space ratio or the lower the porosity, the strength will higher. Okay, and the limiting factor, when the gel to space ratio is 1, the strength will be 234 megapascal for concrete. Okay, so when the concrete has zero porosity, the strength will be around 234, the limiting factor. Okay, so air entraining agent, as we discussed in the lecture of chemical admixtures, so that will introduce the isolated air bubbles in the concrete. So the porosity will be higher when we have air entraining agent. Also, we can see here for the same water to cement ratio, air entrained concrete has lower strength. Okay, so and here shows concrete with different cement content. Okay, different lines, they have different entrained air percentage. Okay, but same trend is when we increase cement content, the strength will be lower here. Okay, but also when the cement content is the same, the lower entrained air percentage, the strength will be higher. Okay, until they cross around 250 kilogram of cement per cubic meter of concrete. Okay, so the reason for that is when the cement content is so low, the workability will be too low. So adding air will actually increase the workability and make the compaction better. So as a result, the concrete has higher air content, will have better stress. Okay, so that's kind of opposite as we think, but when the cement content is too low, the air will actually be beneficial to strength of concrete. Okay, so that's kind of tricky. Questions about this? So because porosity is very important to the strength, and water-cement ratio directly control the porosity. Okay. So water-cement ratio directly control the strength of concrete. This is the Abraham's law, which is more than 100 years ago, shows us the strength of concrete is correlated with water-to-cement ratio. Here the A and B are all constant. Okay. For example, the A value is around 14 ksi, the B value is around 4. Okay, so we can use this equation to roughly estimate the strength of concrete based on W over C, the water to cement ratio. Okay, but I should mention this is fully compacted concrete. Keep in mind when the water cement ratio is become very low, it is very hard to fully compact the concrete. Okay, so if the concrete is not fully compacted, even though the water cement ratio may be very high, but the strength will not be that high because we have a lot of entrapped air or honeycombing in the concrete. So strength cannot be high if it is not fully compacted. The notes here says it does not consider the size, type, texture of aggregate. Okay, and we know aggregate has big effect on strength of concrete. So this is just for the cement paste. Right. So this slide shows us how concrete with a different water to cement ratio, the strength development over time. This is up to 700 hours at early age, right? Okay, so we can see for all the cement water to cement ratio, longer time the strength will increase, but the slope of the curve at different age are quite different. For example, concrete has 0.3 water cement ratio, the strength development at early age is very fast, and also it has higher final strength, later age strength. Okay, based on the curve, we can somehow get an equation. Okay, for example, here the strength Fc is equal to FCU. Okay, FCU means is ultimate strength. U is for ultimate, the final strength of concrete. K here is constant. T is the time, and T0 is the age when the concrete start to get strength. Typically is the time when concrete set, the final set time for concrete. Okay, so here is the measurement of the strength at very early age, which is up to 20 hours. Either use the strength test, which is the dotted line, or the reflection loss, which use ultrasound to send a mechanical wave in the concrete and measure the reflection loss when the sound travel inside the specimen. Okay, so this type of NDT method, we're going to discuss non-destructive testing method in later lectures, can detect early strength change in the early few hours. Okay. Even before the concrete set. Okay. Using compression machine, nothing can be measured before the concrete set. So the water to cement ratio has big effect, right? So, however, for the same age, for example, 7 days, if we increase the water cement ratio, the strength will be lower. Okay, the slope of the curve is also different. Okay. Okay. So this tells us the limiting strength for different water cement ratio is different, and also the stress development for concrete with different water cement ratio is also different. Okay. Okay. So we can see more clearly from this curve. Also for the first day, when the water cement ratio is higher, okay, the slope is more flatter, means the strength development will be slower, okay, compared to water cement ratio of 0.35. So we have steeper slope, so the strength increase will be faster. However, at all water cement ratio increased age, the strength will also increase. So ACI Committee 209 recommend the following equation showing us the moisture cured concrete at any time t as a function of FC28. That means the strength, compressive strength, C is for compressive, 28 means 28 days. Okay, so as a function of FC28 and t is the time. And here shows how the cement composition affects the strength. I think many of things we have discussed before. Okay. So let's look at a higher C3S content. We have a higher early strength but lower final strength. Okay. That is because the heat of hydration are different for different compounds. C3 will be larger than C3S, larger than C4AF, larger than C2S. Okay, so we have more C3S content, the strength at early age will be higher. Okay, but the final age strength will be lower because the hydration product will be less homogeneous. Okay. If we increase the C2S content, that will be the opposite. Okay, because the hydration speed will be lower, we have lower early age strength, but we have more homogeneous hydration product, so that will increase the final strength. Okay, so this is not something new. Fineness, which is the particle size or the surface areas of the cement. If we increase the fineness of cement by reducing the particle size, then early strength and the final strength will both be higher. Okay, Why that's the case? Why that's the case? Let's look at radiated strength. Okay. When we increase the fineness, we have more surface area. That means water will have more contact area with cement particles. So we have more or faster hydration. So that's why for type 3 cement, high radiated strength cement, we have a smaller particle size or high bleed fineness. Okay, for that reason. The reason for higher final strength is because when the particle size is too large, the inner core may not be fully hydrated. Okay. Remember the 3 words when we discuss the hydration process: dissolve, diffuse, and precipitate. Okay. So the water needs to dissolve the cement particles, translated into ions, and iron will be diffused into the pore solution, and then hydration product will be precipitate on the surface or any open space. Okay. When the particle size is too large, the diffusion process will slow down. Actually, when the particle size is larger than 60 micrometer, then the inner core cannot be fully hydrated. Okay. So I think it's we also discussed that before. So today we just refresh our memory. Okay. So let me know if you want me to repeat or you want further discuss of these things. Then let's look at aggregate. Okay. Again, it's old information. Concrete strength will increase with reduce the maximum aggregate size. Okay, because the reason here, reduce the stress concentration. Okay. The stress concentration is caused by different E value of aggregate and cement paste. Okay. Typically, aggregate will be stiffer than cement paste, but that's not always the case. So because the difference in the E value when we compress the concrete, stress concentration will develop at the boundary of aggregate and cement paste. And the larger the size of aggregate, the larger the stress concentration. Okay. And stress concentration will cause concrete to crack first. That's the reason concrete fail. So reduce the size of aggregate, reduce the stress concentration, the strength will go up. Okay, and that's why for high strength concrete we reduce the size of coarse aggregate. Strength of concrete will also increase with higher aggregate stress. Okay, however, this is for high strength concrete only. Okay, and we use in the weakest link series to explain that. I'm not sure if I talked about this before. Have I? Have I mentioned about weakest link series before? Anybody remember? Nobody remember? Okay, so let me go here. Let me do a share of my iPad. Okay. All right, so in concrete we have a cement paste, we have aggregate, and also we have the ITZ. Okay, ITZ is the boundary interfacial transition zone. Okay, so these 3 parts, whichever is the weakest, decide the strength of concrete. All right, so for normal concrete in C, okay, the weakest link will be ITZ. or the paste. So as a result, when crack generated, it will start from the ITG and go through the paste, something like that. Okay, and we call that the weakest link theory. Okay. So for normal concrete, if we increase the strength of aggregate, does not really help, because aggregate is already the strongest part. You increase the strongest, you didn't enhance the weakest link, so the strength will remain almost the same. Okay. Things will change for high strength concrete. For high strength concrete, the ITG will be greatly improved. Okay, because we use low water cement ratio, we use silica film. So in the boundary, in the ITZ, the calcium hydroxide will transfer into CSH. We have denser packing. The water cement ratio is low. The cement paste become much stronger. So for high strength concrete, HSC, the weakest link may become aggregate. So the crack will be go around the aggregate instead. Cement paste, something like that. So when the weakest link is aggregate, and if we improve the weakest link by using stronger aggregate, then the strength will be higher. Okay, does that make sense? All right. Let's continue. If we use rough surface texture, that will also improve the bonding or the ITG between paste and aggregate. So strength will be higher, but that affects more on tensile stress and fracture strength than on compressive stress. Okay, so just keep that in mind. Here we can see if we increase the size of the aggregate, okay, the strength will be lower for concrete with all water cement ratio. However, it is more obvious when water cement ratio is low. Okay, why? We can still use the weakest link theory. When the water cement ratio is high, like 0.70, the weakest link is the cement paste. Okay, and then using different maximum size of aggregate, because the paste is so weak, the crack is always generated there. So we don't see big difference by using smaller or larger aggregate. Okay. Again, this is the concrete with different size of stones, 25 and 10 millimeter. Okay. So 10 millimeter concrete, concrete with 10 millimeter aggregate will have higher strength. Okay. Longer moisture curing, the strength will be higher too. Okay. So that's effect of size of aggregate. Mineral admixtures, we know pozzolanic reaction. When fresh slag are used, the reaction will be slow. So initial strength will be lower, but higher strength, final strength will be higher. Okay. For silica film, because silica film is very small and it is also very, very reactive. So the early strength will not be reduced as in the case of flash and slag. Okay. And also the smaller particle size will reduce porosity and also refine the pore size. Okay, and that will greatly improve the ITZ, and also due to better particle packing. Okay, so silica film is very, very effective when you want to improve the strength of concrete. So use silica film in high strength concrete. All right, so again, this is not something new. Chemical mixtures. This is also old knowledge. Water reducing agent. So when the water requirement is reduced by using smaller, lower water to cement ratio, then the strength will be increased. Okay. But if we do not change the water cement ratio, the strength could still be somehow improved by better compaction, eliminate of large entrapped air, better dispersion of cement particles. Okay, up to around 25%. Okay. For accelerator and retarders, here says no significant effect. Okay, so that means no major effect, but there could be some minor effect. You can think accelerator and retarder as using higher temperature or lower temperature. Okay, so accelerator is similar to increase the temperature. So accelerate the hydration speed. So early the strength will be higher, final strength will be lower because non-uniform hydration product. Retarder will be opposite. Okay, so there's some small effect on strength. Okay, similar as we discussed in the effect of temperature. For air entraining agent, because they will increase the porosity, so strength will definitely be lower. Okay, questions or comments? All right, so current temperature. So current temperature could be including the temperature when we cast concrete, a temperature when we cure the concrete. Okay, so when we do different temperature for casting and curing, blah blah. Right. Here shows us concrete casted, sealed, and maintained at different temperature. Okay. This is only up to 30 days. Okay. So in the first months, we see higher temperature, higher strength. But later on, the concrete cure at lower temperature will catch up. Okay. Actually, concrete cure at 40 degrees Celsius will achieve the highest possible strength because the hydration product will grow slowly. We have more homogeneous hydration product. The chance the concrete has a certain floor will be lower. Okay. But here shows the specimen are casted, sealed, and maintained at indicated temperature for only 2 hours, and then all stored in the same room temperature. Okay, that you see. Even it's only for the first 2 hours, but we still see the big effect. Okay, concrete cure in the first 2 hours at 10 degree, it will achieve a higher strength after after several months. Okay. So again, we see a big effect even for the first 2 hours on later stress. And here shows a specimen was casted at room temperature, then maintained for 6 more hours, and then store in mode at indicated temperature. Okay, so after 6 hours at -9 degrees, because it's frozen, no hydration will goes on, no liquid water, hydration will stop, so strength will not go up after 6 hours. Okay, this only up to 30 days. We can see a higher stock temperature, the strength at early age at least will be higher, but later on the strength will catch up for concrete cure at a lower temperature. Okay. Okay. Here is the steel early age up to 100 hours, around 4 days. Okay. So effect of temperature. Okay, so T is for temperature here. 15, 25, and 35 degrees Celsius, I believe. Okay, and how this temperature will affect the strength at different age. Okay, so what we can see is there's some difference up to 4 days. Okay, like Q at 15 degrees, the strength will remain low for the first 2 days, but they may catch up later on. Okay, 25 and 35 degrees, not big a difference. So here is very clear, showing us many times already how moisture curing, how long you do the moisture curing will affect the final strength. The longer the better, okay, very clearly. All the 4 concrete has the same mixed proportion, so only the curing time is different. So if possible, increase the curing time, okay, because that will ensure we have a continuous chemical reaction going on in concrete. So basically all discussion we did earlier in this class will be something overall, okay? But I don't think we discussed this already before. Testing parameters, how the setup of the compressive machine on the apparent strength of the specimen, okay? So we call that an effect. Okay, so we have a concrete cylinder here. We have a compression machine, and the machine touching the cylinder using a steel plate. We need some treatment on the cylinder, the top and bottom surface. We need to make it smooth by either cut the specimen or we use the sulfur compound to make the top and bottom surface smooth. And then we need to compress the cylinder using different touching mechanism, touching materials. If it's a steel, then when we compress the cylinder, remember the horizontal direction, the concrete will try to expand. Okay, because concrete has Poisson's ratio. You compress in a vertical direction, horizontal direction, it will expand around 20%. Okay? Right. However, the steel will provide the friction or restrain the expansion in the horizontal direction. Okay, so that will kind of prevent concrete from cracking. Okay, I think I need to do the iPad again. Okay. let's say we have a concrete cylinder and we try to compress it. Okay, so the strain under compression we call that epsilon C, and in horizontal direction we have a strain in tension epsilon T. Okay. So concrete has a certain strength. Let's see, this is F prime C, the strength of concrete, which is much larger than the strength of concrete under tension. We call that F prime T. Okay, around 10 times. Okay, but the strain under compression epsilon C is only around 5 times of the strain under tension. So why is 5 times? Because if we assume a Poisson's ratio of 0.2, okay, so strain in the tensile direction will be 0.2 of strain in compression. Okay, so around 5 times of strain in tension direction. And if we assume, the concrete is pure elastic and the E value in all the directions remain the same, then we can conclude the stress under tension, under compression, will be around 5 times the stress under tension. Okay, so let's compare these two equations. The strength is 10 times stronger than tensile strength, but the stress under compression is only 5 times the stress under tension. So you tell me how concrete will crack first. So the tensile stress will be much higher compared to its tensile strength, F prime T. So that tells us the concrete will crack not under compression but under tension instead. Okay, so that's why we see the concrete crack like this. This is because we have a tensile stress. All right. So coming back to this restraint effect. Okay, so this restraint provided by steel plate. Okay, because concrete tries to expand horizontally, and steel closely touch the concrete surface under very high compression, so the friction force is pretty high. Okay, so steel can kind of restrain the concrete from expanding. So that will offset some of this tensile stress. Okay, so that will make the concrete crack later edge. So we're gonna have higher apparent stress. So increase the friction from the, for example, steel plate. So that will increase the apparent stress. Okay. So similarly, if we use Teflon, or steel brush, okay, the friction will be much lower compared with steel plate. So concrete will crack early. So we have lower apparent stress. Okay, question about this. Then let's look at the geometry, such as the length to diameter ratio, and also size of the specimen, how these factors are affecting the strength. If we keep the geometry L to D ratio constant, increase the size, strength will be lower. Okay. The reason will be, okay, we're going to summarize in the next couple of slides. Okay, so increase the size, the strength will be lower. Also, we can see here, keep the same L to D ratio, increase the size, strength will be lower. If we increase the length to diameter ratio, the strength will also be lower. Okay, the reason for that is, again, because of the friction provided by the steel plates. Okay, so the larger L to D ratio, the friction, the restraint effect will be less in the middle part of the specimen because it's longer, right? The lower L to D ratio, the restraint effect will be stronger because the specimen is shorter. Okay, middle part is more restrained. Okay. Here shows similar things. If we increase the L to D ratio, the strength will go down. Okay. Increase the size of the specimen, strength will also go down. Okay. And here is the reason. And again, we discussed this before. We talk about stress concentration, and we know in ITG we could have stress concentration because the different E value between cement paste and the aggregate. Okay. Floor, such as big airways, also introduce stress concentration. And the larger the size of floor, we have larger stress concentration, we have lower stress. And the size of the floor corresponding to the size of the sample. Okay, so smaller sample, smaller floor, lower stress concentration, higher stress. Larger sample, higher stress concentration, higher lower stress. And also, when we increase the sample size, we also increase the amount of concrete. So the chance that bigger amount of concrete has a floor is also higher. Because remember, the concrete strength depending on the weakest link, the floor. So we also have higher chance of floor, also larger size of floor. So that also translates into lower strength of concrete. Okay. The last part says floors are not equally dangerous to all materials. It is dangerous to brittle materials. Brittle materials such as concrete are floor sensitive. Rubber, not so much. Okay, and here, I think is again a old slides showing us the typical failure cracking pattern for concrete. This is because the friction from the steel plate. Okay, in the top and bottom section, because the friction is much stronger, okay, we have a so-called cup cone because the top and bottom is under actually three-dimensional stress. Horizontally it is compression, vertically is also compression, but in the middle part, horizontally that's not too much. Okay. If there's no friction, such by using Teflon, then the crack pattern will be somehow like this because it only under one-dimensional compression in the vertical direction. Horizontally, there's no restraint. Okay. And here shows, how we calculate the E value. The E value is modulus of elasticity. Actually, we have a different type of calculation depending on how you define. Such as this one, this is E chart, which defined as the slope of 2 points. A and B is the point when strain is this much, and B is the stress level is equal to 40% of the final failure stress, F prime C. Okay, and we also have some other E value we can use. And the elastic region is around 1/3 of the first 1/3 of the F prime C. Okay, because in this region, the slope of the curve is almost constant, is almost a straight line. Okay, we can think this region as the elastic region. After that region, concrete will start to crack, and it is not pure elastic material anymore. And here shows how concrete will respond under repeated uniaxial loading. Okay, so after each loading circles, what we can see is first of all the top will go down, which means the maximum stress the concrete can resist will be lower, because after each loading circle we have more cracks. Okay, so concrete become weaker. Also, we can notice the slope after each circle will become flatter and flatter. The slope is the E value, the modulus of elasticity. So concrete become less stiff. Okay. All right. So today we just focus on concrete strength. This is the number one most important property of concrete materials. So we know it is affected by so many parameters such as specimens, dimension, geometry, or even the moisture state when we test the specimen. Okay. Aggregate properties, porosity, size, shape. Okay. Loading parameters, stress type means in the compression, tension, flexure. Rate of stress, how fast do you apply the load, is also important. Okay, we're going to discuss that in the future lecture. Matrix porosity. So porosity, most important, which is controlled by water to cement ratio, mineral mixtures. Okay. Degree of hydration, the curing time, temperature, longer of moisture curing, air content. Okay. Then this is the transition zone porosity. Transition zone means the ITZ, interfacial transition zone, which is the boundary between paste and aggregate. Okay. So ITZ tend to be more porous. So that is affected by, first of all, water to cement ratio, mineral mixtures. If we use silica film, that will be refine the transition zone, reduce the porosity there. Okay. You said bleeding characteristics. If concrete has bleeding, then we're gonna have water layer in the ITZ, so that will reduce the strength by increase the porosity. Okay. How we consolidate the concrete, that will be also a factor. And chemical interaction between the aggregate and cement paste, that does not really happen much, because we typically think aggregate as the inert materials. But if the aggregate is reactive, that will certainly affect the ITZ. Okay. So yeah, so many factors, almost all of the things we discussed so far about aggregate will affect concrete strength here and there. All right, so that's the end for today. Any questions?